In this video, we will do another strong induction example involving Chicken McNuggets. So the problem says when McDonald's first opened, customers could either order 4 Chicken McNuggets, which was a small size, or 7 Chicken McNuggets, which was a large. Part A asks, what's the largest number n of Chicken McNuggets that cannot be formed from a combination of the 4-piece and the 7-piece orders? So, for example, if I want to form 14 Chicken McNuggets, I could take 2 of the 7 pieces and 0 of the 4s, because 4 times 0 is 0, 7 times 2 is 14, and that adds up to 14. So, I want to think about, well, all of these other integers going up from here. Which one of those can I do this for? Which one of them can I not? And I want to give you an opportunity to try this. So pause the video for 3 minutes to try that. Which ones can you form? Which ones can you not? Pause it in 4, 3, 2, 1, pause it. Pause it and try it. All right, so hopefully you did that. Hopefully you paused it to try it. Let's talk about it. All right, so I can do 15 if I take 2 of these 4s and then 1 7. 16 I could do if I do 4 of the 4s and then 0 of the 7s. I'm guessing if you tried it, you probably noticed that 17, nothing seems to work. If you, no matter what you try to plug into these, any positive integers, nothing is going to work. So 17, unfortunately, nothing works. Okay, and then if I keep going, 18, I can get if I do 1 of the 4 pieces and 2 of the 7s. In fact, one of the things that you might have noticed is that if I can get 14, I can definitely get 18 by just adding 1 more 4-piece. In fact, that's exactly what happened. So similarly, I could get from 15 to 19 by just adding one more 4-piece. So this would be 4 times 3 and then 7 times 1. Let's do the same thing for 20. Increase the 4 by 1 and then 7 times 0. So with 21, well, I couldn't get 17. So does that mean I won't be able to get 21? Well, if you played around with it, hopefully you recognize that, wait, we actually can if you do 7 times 3 and then 4 times 0. And the fact that now I can form these 4, I can use the same kind of trick where I increase the number of 4-piecers by 1 to get all of these other ones that to the right. So for 22, it would be 4 times 2 plus 7 times 2. And then the next one's 4 times 4 plus 7 times 1. And then it's 4 times 6 plus 7 times 0. And then it's 4 times 0. 4 times 1 plus 7 times 3. Okay. So, and I could see that, okay, because I can form this consecutive set of 4, I can even form the next consecutive one and the next consecutive one after that. So I'll be able to get everything else after this. So the largest one that couldn't be formed is 17. Everything after that we can form. All right, so now part B. If a customer wants to order n Chicken McNuggets, let's show that this is always possible for all integers n greater than or equal to 18. That certainly seems to be the case based on our experimentation up here. So how do we actually prove this? So let's do a bit of scratch work. If I can form R McNuggets, then we can also form R plus 4 McNuggets, because I just add 1 extra 4-piece to get to it. So if I want to show that this is possible for all integers n greater than or equal to 18, we are going to need, I notice that if I can do a consecutive set of 4, I can get to the next set. So I'm actually going to need 4 base steps, not just 1 this time. And then I am jumping from like 18 to 22 and then 19 to 23. So I am doing a jump of size 4 because I'm adding an extra 4-piece Chicken McNugget. Okay, so that is just some scratch work. Let us get into the proof. So, ordinarily I would probably do some more details in this scratch work, make sure that all of that is in order before diving into the proof. But as we've seen already with these induction examples, they can get a bit lengthy, even now. So for the sake of conciseness, or at least trying to be as concise as possible, I'm going to dive into the proof from here. So let's proceed by strong induction. So indicate the method that I'm using, strong induction on n. The first step is we identify what Pn is, this thing that I want to prove. So for me, I'm trying to show that we can order n nuggets with 4 and 7 piece orders. Okay, I'm trying to show that that's true for all integers n that are greater than or equal to 18. That Pn, this statement, is true for all integers n greater than or equal to 18. Okay, so then we have our base step. We already observed that we're going to need 4 base steps this time. So these are this first consecutive set of 4 things. So I'll have a base step for 18. We can form 18 McNuggets, and then 19, and then 20, and 21. Those are going to be my base steps. This essentially here was some of my scratch work. So how did I form 18 again? Well, we formed it with 1 4-piece order and 2 7-piecers. 19 we got with 3 4-piece orders and 1 7-piece. 20 we got with 5 4-piece orders and 0 7-piece. And then 21 we got with 0 4-piece orders and 3 7-piece orders. Okay, so those are my 4 base steps. Now we are ready for the inductive step. So in the inductive step, we start off by letting k be an arbitrary integer. Ordinarily, k is an element of, whatever set we're trying to show that it's true for. In this case, those are integers greater than or equal to 18. But because we've already demonstrated that it's true for all of these base cases, I can sort of start this off by, I don't have to do all of them. I can just let k be an integer that's greater than or equal to 21 because I already know that it's true for all of them. So I'm going to let k be an integer that's greater than or equal to 21. And then in my strong induction hypothesis, I get to assume that p of 18 is true, that p of 19 is true, p of 20 is true, ... up until whatever k is. ... up until whatever k is. Okay, so I'm going to assume that these are all true. Okay, in other words, I'm assuming that I can form 18 McNuggets, 19, and 20, and up until k McNuggets, just from these 4 and 7-piece orders. Okay, so the fact that I'm saying that k is an integer greater than or equal to 21 is essentially saying that, well, I've already shown it's true from everything from 18 up until 21. So if I only said k is an integer that's greater than or equal to 18, this list here could potentially be stopping at p of 18. But I already know that it goes beyond p of 18 because I already know it goes at least up until 21. That's why it's okay for me to say that k is at least 21. Okay, so how do I state this more formally that, all of these are true? I say assume for all j that are integers, with j being between 18 and k, that p of j is true. So p of j would be the statement that we can order j nuggets with 4 and 7-piece orders. So we can order j nuggets with just these 4 and 7-piece orders. Okay, so, and that's true for any value of j starting at 18 up until k. Okay, so now I need to show that we're going to be able to form k plus 1 nuggets. So let's consider k plus 1 nuggets. K plus 1 nuggets. So will I be able to form k plus 1? Well, I observed up above in my scratch work that we're able to jump back a step of size 4. So will I be able to do that from k plus 1, jump back a step of size 4, and then end up with one of the integers in this list? I really want that, because then I can use my induction hypothesis. So let's jump back a size 4. So note that if I look at k plus 1, and then I subtract 4, if I jump back 4. In fact, let me separate this a little bit more, starting a new thought. So let's put this a bit lower, start a new paragraph. This equals k minus 3. So I'm really hoping that k minus 3 is one of the integers in this list from 18 up until k. Okay. So, can I say that? Can I say that that for sure is going to happen? Because the big thing that I need for that is to make sure that when I jump back, have I not jumped back more than back to 18? So is this, in fact, greater than or equal to 18? Well, yeah, because k is greater than or equal to 21. And if k is greater than or equal to 21, when I subtract 3, it will be greater than or equal to 18. So this is true since k is greater than or equal to 21. That's actually one of the reasons why I really needed to say this, that k is an element, k is a positive integer greater than or equal to 21. So once I got to this part and I was jumping back 4 steps, I didn't go back past the 18. Okay, so we have that k minus 3 is indeed greater than or equal to 18. So by the inductive hypothesis, we can form, or maybe I should say we can order k minus 3 nuggets with 4 and 7 piece orders. Okay, so we can do it for k minus 3. And then, well, what would it take to form k plus 1 nuggets? Well, we just need one more 4-piece order. So by adding one more 4-piece order, we can get k plus 1 nuggets. And that's what we wanted to show, that we would be able to get k plus 1 nuggets. Okay, so that has completed the inductive step. We've shown that we can order k plus 1 nuggets. Then I just got to state my conclusion. So therefore, remember these 3 dots mean therefore by strong induction, the result that we were trying to prove holds. The result we wanted to prove is true. And that completes the proof. Okay, so a couple of notes about this. So we needed strong induction in this problem to be able to jump back more than 1 step. In this problem, I needed to be able to jump back 4 steps to make it work. It turns out that anything that can be proved using weak induction could also be proven using strong induction. But, we usually only use strong induction when absolutely necessary. So, strong induction is kind of like a very high-powered laser beam. And weak induction is, a tool that is still strong. And, often if we can get, something done with, even a simpler tool, we just use the simpler tool. We don't always resort to using that high-powered laser beam to tackle everything. The third big note about this is, the reverse of 2 is true, that if something can be proven using strong induction, you can also do it using weak induction. But it's really tedious to do that in practice, because to show that, you kind of end up proving why strong induction works in the first place, like using weak induction. And that just ends up being often more work than actually trying to demonstrate the thing is true in the first place. Alrighty. So there we have it. Another example with strong induction.